Okay, so we're happy to start the second lecture from Professor Nair, and he will also be present at the Q&A at 4 p.m. for more, if you have more questions.
Thank you, Igor. Okay, so I want to kind of take up where we left things yesterday. What I'm going to do is just let me first remind you a little bit about where we stopped. We looked at the Schrodinger equation and we calculated the vacuum wave function like so, as I described here. I also mentioned that one can calculate higher terms if you try to write down a general series like this, things like F3, F4, things like that. We can calculate. I think I displayed it somewhere. Oh, here it is. Yeah. F3 is here. I haven't shown F4. It's a more complicated expression, but you'll find it in my notes if you want to take a look at it. We then calculated the string tension, and I showed you a formula for the string tension, which was this one here from the lowest order result for the wave function. Okay. So today what I want to do is to ask the question, start by asking the question, what kind of corrections would be there for the string tension? Okay. So what that means is that we should go back here to this expression. We do know what F3 is and F4 is and so on. So if I use this in calculating psi star psi and doing integrals to get expectation values, then effectively psi star psi defines via this F some effective two-dimensional kind of field theory in terms of these variables J. And I want to ask, how do I calculate that integral? Okay. So think of it sort of like a two-dimensional field theory and calculate as you would do in any field theory. Okay. Of course, the first term, we are interested in F2 term because that's what eventually went into the computation of the string tension. We know the first order term in F2. There is also a second order, an E square term in F2 in the scheme of expansion that I showed you. But what we are interested in is, in addition to a correction that enters here, there'll be additional corrections from here that feed back in here when you try to calculate expectation values. Okay, that's what we want to do. Okay, so how do we do that? It looks a fairly complicated thing to do, but it's not too difficult. So that's what I would like to show you. So the first strategy is, we have to have some simpler method of calculating with this action that would arise, or the 2D field theory that would arise from psi star psi. So to do that, here's what I'm going to do. Notice that we have powers of this current that I call J. And there is a cubic term, there is a quartic term, and so on. And what we really need is to be able to compute efficiently expectation values involving these currents. Okay, so to do that, we notice that if I take the Weismann-Witten term, this is part of your integration measure that's going to enter when you do psi star psi and you integrate. And let's say I want to compute correlation functions involving the current, which I have written as DHH inverse. So you just add it with a source term. Okay, and so we want to first look at what this is. Now, C is like a gauge potential again, and I can parameterize it similarly to what I did yesterday. If I do that in terms of some matrix U, which is not unitary or anything, I just call it U, then write C bar as U minus 1 D bar U, then these two terms here can be combined using what I showed you as the Polyakov-Wigman identity last time. I think it is somewhere. I don't remember where it is now. Oh, here it is. So notice that if I have a term like so, in that case, I had U inverse D bar U, but think of it as N. So I have a term like this. I have one of these Weismann terms, combine these two into something like so. I can shift variables of integration then. And then what I'm left with is one of these S's. Okay. So this way, we get an identity that reads reads like this. And so I have, again, the Weismann-Witten action involving U, which comes from C bar. But this actually has a negative sign compared to what I started with. S itself has a negative sign. That's why this is convergent integral on the left. But here is what I have on the right. And I realized that since it is anyway a determinant from our previous calculations, I can represent it in terms of some auxiliary field phi in this fashion. Okay, so this the determinant that arises from this integration here is basically that, which is also the left-hand side via that identity that I showed you. Okay, as a result, if I now take derivatives with respect to C bar on the two extremities of this equation, I see that I can rephrase everything in terms of this scalar field that I introduced. Okay, so that tells me that there is a fairly efficient way to calculate, which is that any expectation value involving psi star psi, take the exponential that appears in psi star psi, replace all the j's by this particular combination, and that is how I can calculate. So this is just the free action for the theory. The F introduces additional interaction to this action for phi, and this is the theory that we can calculate. Okay, so we don't have to worry about how to do integrations with Weismann-Witten actions at the end of the day. It's like a scalar field coupled in some fashion, because there are a lot of interaction terms here coming from whatever F is from psi star psi. Okay, so we do that. There are a couple of renormalizations that would be needed because I introduced this. Without these extra terms here coming from the wave function, if I had just the Weismann term, Z1 and Z2 would be just 1. Okay, but the additional interactions can renormalize, so we have to include that as well. Okay, so once we have that, we can calculate certain things. The only problem is that this F here, this is where I had the little f2 and the little f3 and so on. Okay, this is a series in these currents. The little f3 had a coupling constant E in front of it. F4 will have E square and so on. But the F2 part, the quadratic term here, did not have any parameter in front of it. And that has to be taken care of exactly, even though it's an interaction term from this point of view, because I'll have the square of this object here. So there is a 4 phi term here, phi 4 term here. That has to be taken care of exactly. Okay, so can one do that? And yes, it is possible. You simply have to sum up a series. If I show this term that comes from what is quadratic in F, involving two currents like so, if I show it schematically as this diagram, we had to do a series expansion. I mean, we had to sum up series involving these things here. Okay, and it's not difficult to do. It's when you do that, you find that, for example, the 2-point function for the current takes this form. The things in red come from the resummation I am doing here. But if I drop these red terms here, K over K bar, that is exactly just the current correlator of the Weismann-Witten theory. Okay, so the effect of the wave function to this order is to change what you might expect from the WCW model by this factor M over EK. Okay, and EK is of course square root of K square plus M square. Okay, I call it EK. It's not energy of anything in particular, but it's just a factor that enters. The advantage of doing it this way is you notice that this is actually always less than 1. So the integrand is going to get a suppression factor coming from this resummation here. Okay? And if you think of it as an open vertex, which will be needed for certain other calculations, again, you can show that effectively you get a factorize. Okay, so once you do that, you can do summations. For example, if I have a series of diagrams like this, I can sum up this whole series, put it as an M over E factor, which I show by this red dot here. Okay, so the idea is all the corrections you calculate, you can classify by the number of powers of this M over E that enters into the picture. Okay, so I told you yesterday there is no real expansion parameter in the theory, but what enters is that there is a kinematical factor M over E, which plays the role of an expansion parameter. It enters into the integrands, suppresses the integrands as you increase the power, and that's where the convergence is going to come from. Okay. And once you do that, okay, there are some terms like this also, which will contribute to the renormalization that I showed you, Z1, Z2 factors. But once you do that, you simply classify and group various corrections by powers of M over E. Okay. And here is what happens. There are terms with one power, which we calculate. I'm showing you the correction to the quadratic term because that's what we are focusing on. Okay, so this is the renormalization correction from this procedure that I mentioned. Two powers of M over E, two powers again, there are different terms. And if you keep on doing that, you have to go down quite a bit, up to 4 powers we can do. Okay, and I'll show you why it's okay to stop there. These numbers here are the corrections that enter from these things. Okay, I'm not showing you all the integrals, I just give you the values. Okay, so what is interesting is now let's look at, keep adding them up and seeing what the contribution is really. So if I simply look at the correction to the quadratic term by itself in the y function, which means I'm looking at, I thought I had it somewhere here. No, okay, I probably have it somewhere back here. Yeah, okay, it's basically, I don't see it written here, I think I forgot to write it. F, to recall, has a term that is 0th order in E, and there is a first order term in E. Okay, the first order term directly in F as the solution of the Schrodinger equation, that's a 0th order term I'm displaying to you. Okay, and that term in terms of numerical values relevant for comparison is basically this quantity here. Okay, so it seems like a large correction because what we started with was coefficient 1, but add to it 1.13, that's quite a bit, right? But then when you look at the next term, you find that the first order term is minus 0.58, so that cancels most of it, actually. And so the simplest way to look at it is to do partial sums, okay? So if I only have the 0th order term, it is that. 0 plus 1, the first partial sum is this, second partial sum is this, third is this, and by the time you get to the fourth, it's extremely tiny, okay? So what happens here is that the corrections to the string tension then become very, very small. But why is it small? Not because there is a particular expansion parameter, but because there are also kinematic factors which come into play, okay? And the way it appears, of course, is, cancellations between different terms, each of which can be quite large. So this sounds very much like that there must be another way to repackage this expansion, where these corrections are all built in together and are kind of combined together. And if you ask me what that expansion is, I don't know, okay? Because this is how we found this result, but there will be some way to repackage it, but it's not entirely clear how to do that. Okay, that is kind of an open thing. Okay, so this is what I can say about corrections to this order. It seems very, very small, and there seems to be some kind of interesting kind of organization of the various diagrams that go and various corrections that go in here, but it's unclear how to repackage it in a nicer way. But there must be a way. It is just that sometimes, you discover good results through bad expansions, but, there must be a way to redo this. And I don't know if you know this famous example with, okay, I don't know if I have time to tell you this is but let me explain something. In celestial mechanics, this kind of thing happens very often. And there is a very beautiful classic example of how this kind of bad expansion can finally be repackaged into a good expansion. And this occurs in the problem of the dynamics of the moon. Okay, the motion of the moon around the Earth, you start with a Keplerian orbit, but it is perturbed by the sun. And if you include that perturbation, which is very important actually, you'll find that if you want to do it correctly, you had to go to 500 orders in perturbation theory, okay, which people did, by the way, in the 19th century. But then there is a different way to do it, which is using Hill's equation, and you'll find the whole story written very nicely. Goodsweiler has a Reviews of Modern Physics article. If you look at it, you will see the story. Okay, I'm not saying this is like that, but it may be something similar where you're finding a good result through bad expansions. Okay. Okay, very good. So now I'm going to, I think I forgot to mention. Okay, at the end of the day, you can calculate correction to the string tension formula that I showed you, and you can see that the correction is extremely small. It's very small and negative, and therefore the good agreement that we found yesterday is not vitiated by the corrections, at least to this order. Okay, we haven't done the higher order corrections, so we don't know. That is an open situation. Yes. Sorry. Ek is just square root of k squared plus m squared, where k is a momentum that enters into your integration. That's all. Okay. Ek is not quite an energy. I use the notation Ek, but what it means is that integrals get suppressed by powers of m over e more and more, integrands. Therefore, their contribution finally to the value of the integral itself gets suppressed. Okay, so if you look at it as an expansion parameter, there's no obvious parameter of expansion. It's just these powers that come in. Okay, that's what it is. Okay. Okay, so let's go on to a slightly different topic. We talked about string tension. There is one more. Sure. This is related to the problem of string breaking, which I'm going to talk about in a few minutes. Okay. There is an issue there, and it should, hopefully it will become clear when I do that. But let me first talk about Casimir, and then I'll come to that, okay? Yeah. There is another quantity that is something we can calculate and compare with lattice results, not just the string tension. So I want to say a few words about it, which is essentially Casimir energy, okay? So what you do is you take two parallel plates. It's in 2 + 1, so it's more like parallel wires. Put conducting boundary conditions on it and ask what is the interaction energy between them in the vacuum, okay? So this is a Casimir energy calculation. People have done numerical simulations of that. That's why I'm interested in seeing what we can say about it, okay? So to do that, here's what I'm going to do. I'm going to go back to my inner product, which is this structure here. Again, you have seen this many times by now, but I'm going to do something slightly funny here, namely take this exponential, absorb it into the definition of the wave function. So define a new wave function phi, which carries part of this exponential with it, okay? Of course, if I do that, the Hamiltonian acting on psi and Hamiltonian when it acts on phi will be a little bit different. So you can write down the Hamiltonian as it acts on phi, which is this, okay? So of course, the inner product now looks like a straightforward, L2 norm, square integrability, but the Hamiltonian has this structure. Now, let's take the field H, which I call the gauge-invariant field, and expand it for small values of the field around the origin, around identity, which is the vacuum. And if you just use that and simplify this H prime, I won't show you all the details. It becomes something like this, okay? Sorry, this is H, as I showed you. H prime actually takes a nicer form, which is this, okay? So this phi here is related to the little phi coming from H field through some k-square part. But look at this Hamiltonian. This is exactly the Hamiltonian for a massive free scalar field, okay? So it's not entirely perturbation theory because we have a mass in the problem, okay? So therefore, this is not something that you would see in perturbation theory of the Yang-Mills theory. But nevertheless, this looks like a free scalar field. Plus, of course, there are interaction terms I haven't shown. Now, when you think about Casimir energy, you can ask the following question. I have these two parallel plates, and I'm going to compute the interaction energy between them. If they come very close, you're not going to get anything that you can compare with lattice because there'll be lattice artifacts that come into play. If they're too far away, it's going to die off too much. Again, the value of the potential will get lost in the noise, so to speak. Okay, so there is some intermediate regime, presumably, that we can compare with. And so for that intermediate regime, I'm going to ask the question, can I simply treat it as a free scalar field with a mass, of course, which we calculated yesterday? Okay, so we take this and compute the Casimir energy and see what happens. Okay, the conducting plate boundary condition is this. On the tangential component of the electric field should vanish, which essentially becomes Neumann boundary condition in terms of the field phi. So take a scalar field theory, massive, use Neumann boundary conditions, compute the Casimir energy, and here's the answer you find. Okay, you find something that involves the masses. This is the exponential fall off coming from the mass. There are two terms. These are polylogarithms. X is the distance in units of string tension, and A is an overall coefficient, which is equal to 1 for us in the lowest order, but there are some corrections to it that could arise, which I haven't calculated. So I'm going to leave it for the moment as a free parameter. Okay. Now you can ask, how does this compare with the lattice result? There's a lattice calculation done by this group, Chernow and company. And if you look at this graph, if I try to fit to their graph, you see that it's almost exactly on top of each other. Okay. So the fitting value of A is just 0.97. 1 was the value that we talked about as the lowest order calculation. So even if I didn't do any fitting, just within 3%, I would get agreement. Okay. The important point is not the overall coefficient, but the exponentials, because the exponentials have a fall off rate given to us by the mass that I calculated yesterday. There's no adjustable parameter. We just have to live with it as it is. So the fact that you do get agreement without any input parameters here is actually quite nice. Okay, so that is another observable that you can compare with, and that is coming out to be pretty much as we would like. Okay. Now, what is this mass? I mentioned that this mass actually is also a propagator mass. You see that more explicitly when I look at the formula for the Hamiltonian. This is like a massive scalar field. So if I were to compute a propagator for this phi field, this mass would enter there. And then you can see that it is actually going to act as a propagator mass for the gluon, but in a gauge invariant description. And in that context, that is what is called the magnetic mass in the quark-gluon plasma at high temperature. Okay, so this is actually not an empty statement, that this is a quantity that is of physical relevance to us. Okay, so that is the Casimir idea. Now, related to that, I also want to give kind of the alternate argument, because we saw this Hamiltonian. You might say, well, if this is a Hamiltonian, at least to this order, with just using this term, I should be able to compute the vacuum wave function corresponding to this Hamiltonian. You can do that. It's a free field wave function. You can calculate that. And here is what it looks like. Nothing surprising. Now go back to psi naught, because remember, my wave function had this Bezuminov-Witten term I absorbed this into psi to make a phi. So if I go back to psi, what does it look like? Well, this is how it looks like. And now this gives us an alternative way to think about the wave function. You can say, this is the wave function coming at it from the more perturbative side. Of course, the mass is still there, so it's slightly non-perturbative. But if I take this wave function and ask, I know ultimately the wave function should only involve that current J that I showed you. So find me a function of J which agrees with this result for small phi, small phi, which is here. And the only answer is this, which is our solution that we had before. Okay, so that tells you that there is again some kind of robustness to the form or the wave function that we talked about. Okay, and that actually is kind of important because it also ties in with issues of Lorentz invariance, which I won't discuss here, but it's discussed in my notes actually. Okay, there are some other wave functions other people have proposed after this, variations on the kind of wave function that I showed you here. Let me come back to that a little later because there was a question about the string breaking. And so let me try to take up the issue of the string breaking first, okay? Okay, where is the problem? If I take those wave function, I look at the low momentum limit and simply compute the Wilson expectation value, Wilson loop expectation. That's where I showed you the string tension results. But how does string breaking appear in that language? Well, it's a little hard to see that. So I'm going to come back to that after I show you something slightly different. Okay, what you can do is, there if you're doing, excuse me, if you're doing psi star psi with a Wilson line, you're doing it on a time slice. But you can think more in the language of a Wilson line that is going along the time-like direction, okay, which means you're looking at kind of a charge particle pair, particle antiparticle, and its propagation in time. Okay, if you think of it that way, you can ask, how does the string break? The string breaks because things, if you are in a screenable representation, I can have a gluon attached to it or some number of gluons attached to the propagating particle forming a singlet, and therefore the string breaks, right? So when it breaks, I'm forming a glue lump, as they call it. So the question I can ask first is, can I see a glue lump in this Schrodinger type description, which means you write down a possible wave function for the glue lump and try to see if I can find something that solves the Schrodinger equation, okay? So here is what we do. Imagine that the charge particle, the heavy charge particle representing the Wilson line, I'm going to take it to be an adjoint scalar. So I'm going to call it capital phi. It's not the wave function anymore from the previous slide. It is some scalar field of some heavy mass. Okay, and then I put a gluon, which is in terms of the current, something like d bar j, and I make a gauge invariant operator, act on psi naught, and this is an ansatz for a glue lump wave function. Okay, and this little f here is some arbitrary function. So the idea is try to see if I can impose Schrodinger equation on this wave function and see if I can translate that into some statement about f. Okay, that's not easy to do in general because when you act with the Hamiltonian, you can generate new type of operator structures from it. But in some approximation that I will not go into details here, but some of it is explained in my notes again. You can reduce it to this equation here. Okay, so this is only approximate. Some terms have been neglected here. But you notice that what happens is this is basically a Schrodinger non-relativistic Schrodinger equation. This is the linear potential connecting the gluon part from here to this particle here. Okay, so if I take this equation, solve or estimate the energy, that's going to give me the energy of this glue lump. So even if I don't know how the process of breaking happens, I can try to see where does the breaking actually happen, at what energy does it happen. Okay, so we estimate the energy and I can compare with the lattice results. Here is the lattice result for the two groups here I'm showing here. For SU2, you see the rising potential and then flattening, same thing here. This is kind of where the breaking happens. So you're trying to catch this point here and seeing what is the energy corresponding to that, okay? So if I follow these two graphs, the value they quote amounts in my units, in units of little m, 8.68 and 6.67. So there is some variation in the values quoted. Whereas if you try to take an estimate from here, from this calculation here, you're going to find 7.9. So it's not a great agreement, but it is something not outlandish. It is qualitatively in agreement, okay? But what is more important is the fact that there is some way to think about this now. So we can now go back and ask the question, so if I were to do simply take the Wilson line, multiply by size to psi, calculate it to expectation values, where do I go wrong if I have screenable representations? Where do I see the fact that my string tension calculation doesn't quite work? Okay. And the answer is, from this understanding, it's fairly simple. Why? Because what happens is that when I calculate the string tension by computing the Wilson line, I'm looking at the whole thing as a single connected graph. Okay. What happens is, in the case of screenable representation, is that the Wilson line can break up and little segments can have their own expectation values, so that you will get a lot of disconnected contributions in the expectation value. Okay. It's like you have connected graphs in Feynman graph terminology and disconnected graphs. Similarly here, the Wilson line expectation value breaks up into a lot of disconnected pieces. And that's where the string breaking happens in that language. Okay. That only happens for screenable representations. So the values I calculated for string tension for the non-screenable ones would still hold true. Okay. That is the way it is going to work out. Does that answer what you're asking earlier? Yeah. Okay, thank you. Okay, now one of the things I want to ask next is, I started at 11:30, right? Yeah. Okay, I'm going to say a few more things. So I want to take a look at SUSY theories and Yang-Mills with Chern-Simons added. So before I do that, I want to go back to something I mentioned yesterday. Yesterday I said that the integration measure that I calculated is going to play a central role, that it controls a lot of things. You sort of see its importance from the fact that the Bezzomino term appeared with a coefficient, which is the Casimir of the adjoint representation. Okay, so if I take an abelian theory where the adjoint Casimir is 0, you don't get that Bezzomino-Witten-like action. So there is a big difference between abelian and non-abelian theories right there. Now, you can ask, how does that play into computing various things? So instead of actually doing a calculation, I'm going to give you a simple argument why that term is important in generating a mass cap. Okay, kind of an intuitive argument. And then once we have that, I think we can go back and see what happens with Chern-Simons and so on. Okay, so here's the argument. Let's take a look at how we think about the photon in electrodynamics. Easy theory to solve. You can solve directly. You can see the photons. But let's say you don't want to solve the theory. You just want to come up with an argument why the photon should be there. Okay. So here's how you can do that. You say electric and magnetic fields don't commute. B is like curl of A. Because there's a curl, there's a gradient operator. So the commutator goes like the momentum in momentum space. Okay. So what that means is that if I look at uncertainty principle, uncertainty of E and B for a given momentum value K goes like coupling constant times K, okay, roughly. Okay. I'm not showing all the indices or anything. It doesn't matter for this argument. So now let's say your Hamiltonian is E squared plus B squared, and you're going to take an expectation value for a state which overall carries momentum K. So I'm going to get delta E squared for the expectation value B squared and delta B squared. So here's what it looks like. Okay. So from the uncertainty principle, I can then trade off delta E in favor of delta B, write it like so. Okay. So that's just simple uncertainty principle argument. So now we say we are interested in low energy modes. So let's try to minimize this expression by treating delta B square as a free parameter and see what happens. Well, it's trivial to minimize this. The minimum occurs in such a way where this is of order K. And you can see that if I put the minimum back in here, energy goes like the momentum K. Okay. It tells you that there is a low energy excitation of energy going like momentum K. Okay. That's just the photon. There's no surprise there at all. Okay. But let's try to do that in the present case where we have not just the uncertainty principle, but we also know that there is a different estimate I can do for delta B square. Why? Because delta B square is to be calculated with the Weismann-Witten action in the measure. When you do an integration, like so here, okay, there is an integral buried here, as you can see, because it's an expectation value. So if I'm trying to do it with the integration measure, which carries the Weismann term, let's ignore everything else and look at what is the expectation value of b square coming from the Weismann term. That is just the square of that. I know what is the JJ expectation value. We calculated that a few minutes ago. Where was that? This expression here, without the M over E, just K over K bar, that's what the Weismann term by itself gives you. So you just take that and you calculate the delta B square. It goes like K square because it comes from this JJ commutator, expectation value. So if delta B square goes like K square, that's going to go here, and K square cancels, you're going to get a constant here. Okay, that is the mass gap of the theory. Okay, so what it says is that it's not that you're going to minimize it. You could do that, but that doesn't work necessarily. Why? Because this dispersion going like K square means, to have good approximation, the Weismann-Witten term is acting like a Gaussian of width K square. For low momentum K, it's very narrow Gaussian. So that's going to control everything, not minimization of this expression. Okay. So therefore, this is what is relevant for the non-abelian theory. And you indeed find that there is a mass from here. This term will go like order K square. That's, if you like, the next term in an expansion in powers of K square. Okay. So the emergence of the mass gap is therefore completely correlated with the existence of this measure that I showed you. Okay. So once we have that understanding, it's useful to go and look at what happens in the Yang-Mills-Chern-Simons theory. Okay. So here's what I do. I look at the Yang-Mills-Chern-Simons action. I have displayed this here. There's this K over 4 pi term. K is quantized, as you all know. So this is the theory we are talking about. Okay. Of course, the effect of this term is that if I now look at the commutation rules, electric fields don't commute among themselves. I have E and E bar will go like K. This K is not the momentum, it is this level number here. And the Gauss law also gets a modification. In addition to this term, which was previously there for the Yang-Mills theory, there is this extra piece. Okay. So one of the things we have to do, remember, is to ensure that Gauss law acting on the wave function is 0. That is the condition that we have for what passes for gauge invariance in the theory. So we can look at that, and what it does is the following. If you think of Gauss law as generating an infinitesimal gauge transformation, this is the condition of the Gauss law. Okay, it's not that psi gauge transformed is equal to psi. There is an extra factor coming from here, which arises ultimately because this by itself is not gauge invariant unless, if you have a boundary, it is not gauge invariant. Therefore, if you look at 2 time slices, we had to deal with what happens on the upper time slice and the lower time slice. Okay, so that is the effect that is buried here. So this term creates an extra piece here. Okay, so we can then write down the solution. It's once again, because of the structure of this, notice that there is a d bar with this term here and a d theta with this guy here. Both of these can be related to the Weismann-Witten action again, and variation of that through that identity, the Polyakov-Wiegmann type identity that I mentioned. So you can write down the solution. Okay, so here is how it looks. Now it is a little more involved than just a function of, what is going on? Something happened, sorry. It's more than just a matter of something being totally gauge invariant, like so. It's a function of h, that's gauge invariant. There's an extra phase factor. This is a phase factor because these are conjugates of each other. So this is really imaginary up here, and that's a phase factor. Okay. Is that something surprising? No, not at all, because if you have a theory with a velocity dependent potential, which is the case of the Chern-Simons term, then you know that there are phase factors in the wave functions. Okay, the wave functions cannot always be cannot all be chosen to be real, or yeah, real if you have velocity dependent potentials. So that's where this comes from. Inner product is, of course, as before, because the integration measure of the gauge fields hasn't changed. It's just what it was always, right? It's just defined by the geometry of the space. It's space of gauge potentials modulo gauge transmissions. So that's completely given to you. Okay. So if I now try to take this solution for the wave function and add an extra piece here by hand just to redefine a new wave function phi, then here is how it looks. Okay. So that means the new inner product in terms of the phi has the old Weizmann term, but another one level k Weizmann-Witten, and this arises from the Chern-Simons term, this extra piece. Okay. Why is this such a nice thing to do? This is a good thing to do because, well, first of all, let me say, this result is true independent of whether I have a Yang-Mills term or not. Pure Chern-Simons theory, this is the inner product. Chern-Simons theory with Yang-Mills theory, this is still the inner product. Okay, the difference only arises when you talk of Hamiltonians and so on. The inner product is the same. In terms of phi, I can write down the Hamiltonian. So what happens is I have redefined some wave function like this. So if I look at the Hamiltonian of the theory, acting on psi, I push it through these factors here and see how it acts on phi. Okay, because that's the one with an easy inner product. If I do that, it has exactly the similar structure as I showed you before for the Yang-Mills theory. Okay, almost exactly the same. You may recall that there was a J delta delta J term, and this omega was the OPE, the operated product expansion kind of thing for the currents, and there was a second derivative term like so, and then this term. It's almost exactly the same, except for one difference, that instead of being the current J, it is a scale version of the current J, where I have this level number appearing now. Okay, so therefore, other than that, there is not much difference in the Chern-Simons theory compared to pure Yang-Mills theory. Okay, but of course, the physical consequences are very different, because if I know that this is a structure, this is very similar to what we had before. I can solve Schrodinger equation using this again and find the ground state wave function which takes this form. Okay, that's great. So even if I take this, this is almost exactly the same structure as I had before. But nevertheless, if I now take the small momentum limit, it looks like this. And you might say again, am I not going to get confinement and string tension? But the answer here is no. Why? Because even though all this looks like the pure Yang-Mills, notice the integration measure has this K piece here. So if I write in terms of just the integration measure for gauge fields, I have this thing still hanging out. Okay, and this is going to say that the area law no longer applies. The Wilson line now does not obey an area law anymore. Okay, so how do you understand this in other ways? I mean, since we came so far, you can ask, is there some other way to understand this? And the reasoning is fairly simple, right? If you think of Chern-Simons theory in the language of conformal field theory, remember Chern-Simons theory, if you give me that, then on the boundaries of the space that I'm defining, the Chern-Simons theory becomes a conformal field theory, a Weizmann-Witten theory, right? So in terms of that, if I have a level number K, I don't have, what are the operators of interest? I have all the primary operators I need. I have the identity operator, but I also have other primary operators in the theory, taking spin values all the way from whatever it is up to the level K. Okay, if it's AC2, I go spin values up to K. Right? So there are other states in the theory that are coming into play, and these states can screen any Wilson line that you put in there. That's how it works out. And therefore, the fact that you can see it either by directly carrying out this integration, this is going to cut off the integral and give you a Wilson line that does not obey the area law. However, another way to see that is it arises physically as screening because there are these additional fields possible, which are the primary fields from the conformal field theory point of view, which can come and screen the Wilson line. Okay. Now, once we have that, we can see whether we can say a few more things about it. So what I'm going to do now is to talk a little bit about supersymmetric theories. How does this help with respect to supersymmetric theories? So I'm not going to go through the full calculation. One can do that. You can take the supersymmetrized theory and go through defining fields and gauge invariant fields and so on, as I showed you. But there is a slightly different way to do that, a way that avoids a lot of detailed calculations. And that is the argument that I would like to give you. Okay. So how do we do that? Well, the key point here is that the integration measure here is the same both for Yang-Mills-Chern-Simons or pure Chern-Simons theories. So the strategy we are going to use is how do we fix that measure? If you have some way to fix the measure without, in an indirect fashion, then we can use that without actually having to go through detailed computation to see what the implications are. Okay, so that's the argument that I would like to talk to you about. Okay, so how do we do that? So let's consider a level K SUN Chern-Simons theory, but with some point particles added, which of course, if you think in space-time picture, would be Wilson lines. Okay, so this is goes back to the original calculations done in the famous paper by Ed Witt in 1988 and so on. So let's look at the Chern-Simons theory, quantize it with point particles added, and look at the two-particle state. Okay, the two-particle state is obtained in this fashion. This M is a matrix that I introduced. And why do I need these factors? This is a particle and its conjugate. I need that because the Gauss law contains, in addition to just the usual terms, a term that contains a charge particle. Okay, the charges of the particles. Okay, so this is the solution that I found, and N is some overall factor that I have that I can add. I mean, this is not fixed by anything at the moment. Of course, if you give me a state like this, I can normalize it, and this should be the normalization condition because M dagger M is H. Effectively, I'm going to end up computing the two-point correlation function for this matrix H that I introduced earlier. What is a measure of integration? We know that it is 2CA here, but I'm going to leave it free for the moment because I want to show you how one can indirectly arrive at that result. Okay, I'm going to call it K tilde for now and leave it like this. Now, the point, of course, is how do I fix N and how do I fix this correlation function? Okay, fixing N is easy because we know that we have solved the Gauss law here, but there is one more equation to solve, which is that there is a Schrodinger equation for the problem. This is pure Chern-Simons. So the Hamiltonian for the Chern-Simons part is 0. But once I add external particles, charged particles into the theory, the coupling of the gauge field to the charged particle, that produces a non-zero Hamiltonian. Okay, so that Hamiltonian should be such that I should have the Schrodinger equation, and therefore the equation for N is basically the Schrodinger equation for that theory. Okay, what does that equation look like? It is going to tell me how N depends on Z1 and Z2, the positions of these particles that I introduced. And that equation, the Schrodinger equation, becomes what is known as the Knieshnik-Zamolodchikov equation from the point of view of conformal field theory. Okay, and that equation takes the form, there is d over dz, and then there is a charges enter here, acting on N is 0. Okay, that's the equation. It's a fairly simple equation, but this equation, the KZ equation, is what determines this factor here, but it's also what determines from the conformal field theory point of view what are called conformal blocks. Okay, this N is basically like a conformal block of the theory. Now, what is kappa here? Kappa is our level number K of the Chern-Simons theory, but there is a renormalization effect. It is getting an adjoint Casimir added to it. Okay? This renormalization is well known. It can be shown in many different ways. There is an argument given to it in Witten's paper that I mentioned. There are other ways to see it also in different ways. Now the problem with this solution is, with this equation is that if you solve this and find n, there is going to be some non-trivial z1, z2 dependence that you can read off from here and you solve it. But if I put that in here and I want to set this to 1, you can see that there's going to be a problem because the z1, z2 dependence must be exactly cancelled by this correlation function for it to be able to become a normalizable state set to 1. Okay. So that means this correlation function in the Hermitian theory that I'm talking about here, with the Hermitian matrix H, should be such that the absolute square of n is cancelled. Okay. So that's what I'm saying here, that therefore it requires the Kz equation to have to, this should obey the Kz equation with kappa replaced by minus kappa that is needed. Okay. On the other hand, if you go back and look at the work of Kawetsky and Kapanen, this I'm not explaining it in great detail because that's a long saga. When you have a Hermitian matrix model, a Hermitian Bezemanov-Witten model, level K tilde, they can show, and it's an analytic continuation argument that, oh boy, this really, if I press too hard on it, it seems to go back. Oh. Okay, so what happens is that if you give me level K tilde, then for the Hermitian theory, you get the correlation function is exactly the same as the correlation function of the SUN theory with the level minus K tilde. Okay, this is the result that comes from analyzing the conformal field. So if I put that together, I know that this should be described by SUN level minus K tilde, but it should also, for this normalization purpose, should agree with minus kappa. So that means if I take this minus K tilde in the SUN theory, add the renormalization shift, that should be minus kappa plus the renormalization shift E, which is this. Okay, so this equation, if you solve, putting CA here and CA here, you find that K tilde should be twice CA. Okay, so the result that we found before can be obtained like this. So this is an indirect argument, but the good thing about the indirect argument is that if I know how that renormalization shift works, this last equation tells me how to compute the integration measure for any of the theories that I'm interested in. Okay, this is for the Chern-Simons theory, but I can add, as I told you, the measure is unchanged between Chern-Simons theory and Yang-Mills Chern-Simons theory, so I can use it for the Yang-Mills Chern-Simons as well. Okay, or even pure Yang-Mills theory, just put level number K equal to 0. You can use it for Yang-Mills also. So if I try to do that in terms of various supersymmetric theories, here is what we find. Renormalization shift to the level number, you can also calculate by Feynman diagrams. That's why it is easier to, that is how we sort of avoid having to calculate this, if you like. And it was originally done in the non-supersymmetric case by Pisarski and Rao, and then extended to supersymmetric theories by these gentlemen here. So the inner product then for various kinds of supersymmetric theories takes this form. Okay, I'm going to write it still as K tilde. There will be some integration over fermion variables and so on, and here are the wave functions. So if I have no supersymmetry, n equal to 0 case, our old result K plus 2 times CA. K comes from the Chern-Simons. This is there from the beginning. So if I don't want the Chern-Simons, I can go back to pure Chern-Simons, pure Yang-Mills, put K equal to 0. If I take the n equal to 1 theory, then here is what you find from this equation, previous equation here. You just put the renormalization shift found by these guys, and you find this value. Okay, what does that tell us? The n equal to 1 theory, because the measure contains K plus CA, even if I put K equal to 0, look at pure Yang-Mills theory n equal to 1, I'm going to find that there should be a mass gap. Why? Because I gave you an independent argument for the mass gap, which is entirely controlled by the integration measure. Okay, so therefore we would conclude therefore that the n equal to 1 theory, superangles theory, should have a mass gap. Of course, I cannot quite put k equal to 0 for n equal to 1 theory because there is a certain parity anomaly and so on. Therefore, the lowest k value I can choose to be consistent with supersymmetry, to make a consistent theory with n equal to 1 supersymmetry, is k equals 1. So that theory has a mass gap. Okay. What happens if I go to n equal to 2? Then from this argument here, you'll conclude that there is no shift here. K tilde is just k. And if I put the level number k equal to 0, I find that the pure n equal to 2 superangles will not have a mass gap in 2 plus 1 dimensions. Okay. So those are conclusions we can reach just based on the structure of the integration measure. I should point out that the n equal to 2 theory, it may not have a stable vacuum. There are arguments to suggest that the superpotential may run off and create an instability, but that is not something we can see from just the measure argument. You can, of course, ask the question, I gave you a kind of a roundabout argument without having to calculate anything using the measure, but can I actually see that if you don't want to do that and you simply take the, say, n equal to 1 superangles theory, sit down and do the various Hamiltonian quantization that I showed you earlier, what do you get? Do you get results which agree with this? And the answer, of course, is yes. I just didn't want to go through all that detailed calculation for you. That's all. Okay. So all the results you can check directly also by explicit calculations. Now, the conclusions that I have derived here, I have talked about here, they are also agree with other methods. Mithat has worked on it, Gomes and Russo, and so on. Okay. Now, I want to make a couple of comments more. How much time? I have 15 minutes more or so. Is it? Oh, 20 minutes. Oh, plenty. Oh, that's plenty of time then. Yeah. Okay. Very good. Okay. So let me show you something else. I want to ask one more thing, which is, we're talking wave functions. Okay. I try to convince you with all these results that wave functions are not so bad, right? That there are good things you can do. But there's one thing that wave functions are extremely good at, which is that if you want to compute something like the entanglement in a quantum field theory, then wave functions are the kind of things to look at, right? Because entanglement is basically something that you phrase always in terms of wave functions, essentially, okay? So you might ask, can I say anything about entanglement in the 2 plus 1 Yang-Mills case? Okay, so I'm not going to go over the details of the entanglement, but I want to point out one particular aspect of it, okay? And that's the following. You can sort of try to understand what is the nature of the entanglement by looking at the Maxwell theory already. So I'm going to go a little bit over the Maxwell theory, and then I will rephrase things in terms of the Yang-Mills theory also, okay? So let's say we want to try and calculate or quantize Yang-Mills theory and try to write down a Hamiltonian path integral. How would we do that? Okay. We would have, of course, the action for the Yang-Mills theory. We, of course, need the Gauss law constraint for the theory. So introduce that via a delta function. You need a conjugate gauge fixing constraint normally. So you introduce that with another delta function. But when you have constraints like this, the general rule of Hamiltonian quantization is the determinant of the Poisson bracket of the constraints should also enter into the measure, okay? So the measure of integration when you have constraints is, if you may have seen this before, but if you haven't, you put one set of constraints here, you put the other set of constraints here, and then you also have the determinant of the Poisson bracket between the two. That is what goes into the integration measure when you have a theory with constraints that you want to quantize in the Hamiltonian language, okay? So those are the three things I write here. Constraint 1, constraint 2 with delta functions. This is the determinant of the Poisson bracket of these two guys, okay? And then, of course, you have the phase space integration measure because this is phase space path integral. Okay. So now what happens is the following. Imagine I have the theory defined in some large volume, and I'm going to divide that into two regions, V1 and V2, with some common interface. Okay. Then if I look at this determinant here, it's defined in the large volume, and I'm trying to divide it into two different pieces. And there is a very nice formula for doing that, that is known as the BFK gluing formula in the math literature. Okay. And what does it say? It says that the determinant over the whole volume can be divided into determinant in volume V1, determinant in volume 2, V2. But there is an extra term that lives on the interface, which is the determinant of what I call M1 plus M2. M1 and M2 are simply the two normal derivatives acting on the Green's function region 1, that's M1, the same in region 2, that's M2. These Green's functions are calculated with Dirichlet conditions in each of these regions. Okay. This operator has a name. If you think of it as a kernel or as an operator, that's known as the Dirichlet-Neumann operator. Okay. And the theorem says basically that if I take the product of these three things, namely determinants in the subregions, and then an extra determinant of the Dirichlet-Neumann operator on the interface, that's going to give me the total determinant. Okay. So this is the gluing formula. So if I decompose this by the gluing formula, this determinant, I'm going to get these three things here. What about these two guys? If I look at it and decompose these in terms of separate regions V1, V2, you will find this. So what happens is this multiplied by the phase volume. These factors exactly cancel this, and all the determinants disappear from the theory. Okay. Yeah.
This final determinant term, determinant of M1 plus M2, is it specific to 3 dimensions?
No. Sorry. I should say the BFK formula is very general. You start with any Riemannian manifold in any number of dimensions, and for simplicity, I will take Euclidean signature. Then think of hypersurfaces which can divide it into any number of regions separated. And then you ask the question, determinant over the whole space, how does it relate to determinants defined in each of the subregions? So the determinant of the Laplace operator in the whole space is the product of determinants in each of the regions times interface terms, which are determinants of Dirichlet-Neumann on each of the interfaces. Okay.
I'm asking because depending on whether one is in odd or even dimensions, there's sometimes the issue of entanglement anomaly.
Yeah.
And this is not related to that, I suppose.
What do you mean by entanglement anomaly?
No, in the sense that I think that would that pertains to some duality when with the path integration. Probably it's not related.
Yeah, I don't know. Okay. It may be related, maybe not. Okay. This is related to edge modes. That is what I'm going to say in a few minutes. Okay. If that's the issue, then it's definitely related. Okay. Okay. So what I was going to say was these things cancel completely. But if you look at where the cancellation arises, remember, this is Gauss's law, and it's a conjugate constraint. So enforcing Gauss' law in region 1 is where you're going to pick up this determinant. Enforcing Gauss' law in region 2 is where you're going to pick up this one. And this comes from enforcing Gauss' law on the interface itself between the two regions. Okay. So now the important thing, of course, is that if you're trying to, it's not too difficult to see, because if you see, for example, if I use Maxwell's theory and use my parameterization that I showed you yesterday, is di theta plus epsilon ij dj, I think I call it phi or something. Notice that del dot A is basically d square theta, and then you're going to get a Laplace operator there. Okay, and because it's in the delta function, you get an inverse Laplace operator, the inverse determinant. That's where these things come from. Okay. So anyway, the point is that this term here is crucial because it's cancelled by enforcing Gauss law on the interface. But on the other hand, if you're going to simply integrate over fields in region V2, see, from the point of view of a theory defined in V1, modes on the edge that you have generated by Gauss law are physical states. Because remember, at the beginning of my talk yesterday, I mentioned to you, you enforce Gauss law always with a test function that vanishes on the boundary. So if you are forever living in region V1 and you try to set up your theory, you're going to allow only test functions which vanish on the boundary of V1, which includes the interface. Therefore, the value of, so if you do gauge transformations which don't vanish on the interface, from the point of view of V1 and V2, they're actually physical modes. These are the edge modes that you just mentioned a few minutes back, okay? So if I'm just integrating out degrees of freedom in V2, for example, then there is no enforcement of constraint that enters. So this term is not canceled out, and there will be a leftover piece if you look at the Hamiltonian path diagram, okay? That piece is exactly what is sometimes referred to as the contact term. Many years ago, Dan Cabot calculated this contact term by looking at entanglement in a gauge theory, where, of course, he didn't do it in this language, Hamiltonian language. He was trying to set it up as a path integral with replicas, the standard replica trick. I think we saw some of that yesterday. So he was able to calculate an extra term that arises in gauge theories, which he called the contact term. The contact term is basically coming from this fact that there is a leftover determinant from the BFK formula, okay? And so that gives you a Hamiltonian way of understanding the contact term. It also gives you a physical sense of where it comes from. It's because there are edge modes that don't necessarily get canceled out, okay? Yeah. Okay, now I'm not talking of other terms that arise from the wave function here because I wanted to focus on this for a reason I will tell you in a minute or so. Now, let's think about this in the non-abelian case. And you can say, well, I phrased this in terms of gauge fixing and so on, didn't I? But all of yesterday, I was telling you that we don't need gauge fixing. You can factor out gauge transformations and so on. So how do I square it with what I said yesterday? Well, there is a simple way to think about it. The gauge potentials that I gave you in terms of M and M dagger can be viewed, and I think I mentioned this yesterday also, as a complex gauge transformation of this particular choice of gauge potentials, okay? It's a complex gauge transformation, right? But nevertheless, it is that form. And that means that if I choose as a complex gauge fixing condition, M dagger equal to 1, then I can rephrase what I said yesterday, again, formally in the language of gauge fixing. Then I can compare with what I just showed you here in terms of setting up the Hamiltonian path integral. So what then is the contact term that I mentioned to you? It will, again, is the discrepancy of the determinants that enter. But of course, the determinants now are fully covariant DD bar. So determined over the full region and determined over the subregions, this discrepancy is what would appear as the contact term or the extra contribution to the entanglement entropy. Now, why is this interesting? Just one, yeah. Sorry, the upstairs, you mean? Yeah, that's right. So there is a discrepancy here because, as I showed you from the BFK formula, if I divide this by the separate regions, I have this leftover. Okay, so that is the leftover piece which would serve as the extra contribution to the entanglement in the problem. Okay, does that answer your question? Yeah. Okay, so so why is this interesting? Well, here is the point. You see, when you talk about entanglement, if you have a theory that is massive, entanglement tends to die out because the mass basically cuts off correlations over longer distances. Okay, you can see that explicitly even for a simple scalar field. Just calculate, you see that indeed it is indeed the case. So you might say, if I give you gauge theory where there is a mass gap, which is what I have showed you in terms of the 2+1 case, then should I worry about entanglement because there is already a mass? And so if I look at, over separation, there are no correlations that extend over longer distances. The answer is yes, there is still an entanglement contribution because this one does not suffer from the mass gap. The contact term is there as it is for the massless theory because it has only to do with how you factor out gauge transformations. Okay, so therefore this contribution persists, and it would be interesting to calculate this. Trivially, if I ignore the gauge fields in the covariant derivatives here, it's exactly what happens in the abelian case. But what would be more interesting is to calculate with the wave function that I showed you before, which we haven't done. Okay. Now, since I have 2 more minutes, or maybe 4 or 5 more minutes, I can just quickly tell you a little bit about, I just want to be fair to other authors. So let me just say that although I showed you the wave function by solving the Schrodinger equation, there have been a couple of alternate proposals which came up after that. And so I want to tell you about 2 of them. One of them is due to Ley, Minich, and Yelnikov. They proposed essentially something similar to what we had, but using d bar j and d bar j. But the kernel, for me, which was that 1 over square root of m plus k square plus m and so on, that's replaced by a more complicated thing. You call this operator L, then the Bessel functions, a ratio of Bessel functions of these things is used. Okay. Now, if you ask me where it came from, well, there is an argument for that. They show that they try to write it as a power series involving powers of L, and then they try to calculate the action of the Hamiltonian on it. The lowest order agrees with what I showed you before. The first order they can calculate. Beyond that, it is difficult to calculate, but they made an ansatz for it, which may be true, may not be, but they were able to then sum it up and write this proposal. If you actually match this to the wave function that I showed you, they're very close to each other. So they're not very different in terms of momentum dependence or the kernel. Okay, so that's one of the proposal. On the other hand, on the good side though, they have actually used this to calculate some glue ball masses, and this is the calculated value. These are the lattice values, again taken from Tepper's group. These are the values involved here, and you can see that they're not, I mean, some of them are fairly close, like these ones here, but some of them are a little bit further off, like these ones here, and so on. Okay, so it's not too bad, but it's not, not everything is on the dot necessarily. Another wave function which people have tried is a different way to write it in terms of some covariant derivatives. This is the lowest eigenvalue of the d square operator, and they also compare that with what we have, and again you see that this kind of turquoise line is the result that I showed you, and this purple line is their result, and I don't think you can really distinguish the 2 curves. Okay, it's pretty much close to each other. Okay, so there are other ways to look at it, but neither of these is a solution of the Schrodinger equation per se, and for that reason, one has to be a little careful in how these are used. Okay, now let me just basically conclude. I just want to say, I gave you a story with Hamiltonian quantization and how to use wave functions, okay? But there are clearly many, many open questions. And, my purpose was to hope that some of you might actually take up some of these open questions. There are a lot of open questions in loose ends. I just say a few words here. Crucial, of course, is, I mentioned how the corrections come into the picture, and is there some way to reorganize that? There is clearly more work that one can do on supersymmetric theories. The non-abelian BFK theorem, even in mathematics literature, it has not been really worked out in detail. It would be nice to see what it is, because we now have a way to look at it. Adding quarks, glue balls, things like that. There is some work I have done on an effective action description of the same theory. Everything I told you was Hamiltonian. So you might ask, well, what if I don't like Hamiltonians and at the end of the day, I want to see things in terms of some sort of covariant description? Can I do that? After the fact, it has been possible to work out some sort of covariant description. I didn't have a chance to talk about it here, but it's not, I mean, I will refer to it in the notes, so it should be okay. Another interesting thing is to do it on a torus rather than flat space, because if you have a torus, you have the modular parameter, which allows you some flexibility and control over how you can stretch and so on, different directions. You also have periodicity, so you might be able to compare something with finite temperature and so on. Okay, so that's an interesting thing to do also, which, I mean, so there are many, many open questions, but what I really wanted to show you is basically one single fact, that there might be, if you push it hard enough, there could be some good results you can get out of the Schrodinger representation. Okay, so thank you for your attention.
Yeah, thanks a lot. Questions? Yeah.
One of the alternate things I showed you was a variational calculation. Okay, people do variational calculation, but I'm a little wary of variational calculations. And the reason for that is something I mentioned yesterday, that if you want a theory with Lorentz invariance, you cannot have vacuum energy. Any variational calculation is going to give you a finite vacuum energy. Now you might say, what's wrong with that? Well, it means that you're starting with Minkowski space whose isometries mean Lorentz transformations. You are ending up with something that doesn't quite match with that. So it's a little bit uncomfortable for you. Okay. Yeah. I think Richard Feynman long ago criticized variational approaches in field theory for similar reasons also. Okay.
Yeah.
I didn't quite hear. Yes, yes. I think so, yes, but I don't think it has been explored very much. Okay, the only things I know are people have calculated on just flat interfaces. Okay, I have done a calculation of that, not in the context of entanglement, but actually just that interface term I have calculated in the case of an interface which has an extra hole in it, for example, which is not totally different geometry, but it has additional boundary contributions. Okay, so yes, the general answer is it does depend on that. Okay, and that would be an interesting thing to calculate, actually. Yeah.
Yes.
We have already answered this.
Non-Freudian case, great correlations, you showed that you expect some kind of additional. There's breaks there when I tried to apply it for Yang-Mills cluster, where I wasn't sure whether.
Yeah, there is a difference because the Hamiltonian changes, right? Because Yang-Mills is added, the electric field is no longer the canonical momentum. So if you formulate the Hamiltonian, it changes a bit, actually.
And if I trace that through, I'll see no mass.
You should be able to see that, actually. Yeah. Okay. Not that there is no mass gap. There will be mass gap, but there's no confinement. Remember, additional Chern-Simons already gives you mass, right? Even in perturbation theory, right? Yeah.
Okay. Well, we'll have more Q&A at 4 p.m. So let's thank Professor Nair.